Welcome back to the lessons on projectiles. We're doing part A questions. My name is Kieran Mills and I teach applied maths at the Academy. In lesson 2, I'm not actually going to do anything new. I'm just going to do slightly more complicated questions from the Leaving Cert. I'm going to start off doing Leaving Cert 2016, 3-part A. So, a ball is thrown from a point A. Remember, if it's thrown from A, that's my starting point. So I will call that the origin. So A is 0, 0. You can see it's thrown down. When you go to the right, that's positive. When you go down, that'll be negative. So its initial speed, this time, in the y direction will be negative. Signs are very important when you do these problems. So we're trying to fire at a target T, but it overshoots and hits a point B on the ground. T, they're telling me, is 21 meters from O. So I've overshot it by a little bit. The initial speed is 25 meters per second, and the angle is 30 degrees below the horizontal. What are they asking me to do? They're asking me to find the time taken for the ball to travel from A to B. So, same technique. Do your table, UX, AX, SX, and do the same on the Y side. Now, the table is for what? The table is for arriving at B. That's important. It's at B. So I'm going to write down what are the coordinates of B. Well, the coordinates of B, how far to go out to the right? Well, I know to go out to T is 21, but I overshot T, didn't I? So I actually don't know what the distance is in the X direction. So I'll just call that SX. And what about the Y direction? Well, I started here and it fell a distance of 17.4 meters down. So I've got to make that minus 17.4, as you would do in coordinate geometry. So now let's fill in my table. So UX, it's going to the right, so we take that to be positive, is 25, and the X component is always cos. 25 cos 30 degrees. Put that 25 cos 30 into your calculator, and I will get 25 root 3 on 2. Should I decimalize it? No. I mean, if they start getting too complicated, we will decimalize it. By and large, we just leave it like that. What's the Y component? You've got to be careful about the Y component, because you can see that missile is being thrown down. So down is negative. So it's going to be minus 25 sine 30. Put that into my calculator. I get minus 25 halves. So put them into my table. UX, 25 root 3 on 2. And UI minus 25 halves. AX and AY, always the same, aren't they? We're talking about B. What's SX? Don't know. What's SY? Minus 17.4. So they're asking me to find the time. Well, have a look at it. On the Y side, you have full information. So therefore, I'm going to apply my equation, S equals UT plus a half AT squared. And I'm going to apply that in the Y direction. Fill in the numbers. SY is minus 17.4. UY minus 25 halves. T plus a half AY. You know what that is now, don't you? A half of AY is minus 4.9. T squared. That, once again, quadratic equation in T. So see if I can solve it. Well, I'm going to bring on my side. I want a positive t squared, so let's bring them to the left. So it's 4.9 t squared. I'm going to jump that to the left, so it's plus. As everything else is decimalized, why don't I decimalize that? It's a nice decimal anyway. It's not repeating. So that's 12.5t minus 17.4, and that's equal to 0. Now, that may be factorizable, but I really don't want to find out. The numbers look a bit nasty. So if in doubt, just go straight to your formula. So you know what your formula is. You write down your ABC. Coefficient of t squared is A. Coefficient of t is B. And C is the constant, minus 17.4. And then you put them into your quadratic formula. It's a quadratic in t. So t is minus b plus or minus the square root of b squared minus 4ac divided by 2a. So put the numbers in. Minus b is minus 12.5. Plus or minus. Sometimes there are two answers. But there's one thing I do know. I know that time can't be negative. So that's already negative there. So if I use the minus part, the entire top will be negative. So I can ignore that minus in this particular instance. So I just have to use the plus part. Plus b squared 12.5 squared minus 4, a 4.9 by c minus 17.4. Divided by 2a, 2 times 4.9, it's actually 9.8. So put all that into your calculator. And you know, when we're doing these questions, you know, don't be passively looking at it. Have your notes in front of you, be doing the questions, have your calculator there. Don't be watching me doing it on my calculator. You have to do it yourself, essentially. So press the fraction button and off you go. And I get an answer of t is 1 second. So actually, it would have factorized usefully. You know, if you're good at factorization, you can go ahead and do it. But if in doubt, just go to the formula. So it takes 1 second to last. Now, continuing on with that question. I now want to find the distance TB. Well, you know that TB is? It's that extra distance, isn't it? You've overshot the target T by a certain amount. So now I'm going to use the SX formula. SX will give me the entire distance from O to B. So I find SX. You know that's an easy equation, don't you? There's no AX in it. So that's UXT. UX is 25 root 3 on 2. Multiplied by 1 second. Remember, time on the y side, that can be carried into the x side by 1. So my answer is 25 root 3 on 2 meters. And then obviously to find that distance TB, that extra distance, the entire distance from O to B is what we called SX. That's 25 root 3 on 2, and we take away the 21. That looks like a bit of a mess, so we'll probably decimalize that 1 or 2 decimal places. They never tell you, so it's up to you what you actually do. Press my SD button. I'm going to go 2 decimal places, 0.65 meters. Now, it's still not finished. You know, it's a tricky enough question. The last part is involving the other equation I haven't talked about. All the time I've been using S equals ut plus a half at squared. Well, there is an equation that you have to use called v is equal to u plus at. So it tells me for the last part, the point C, that point there, is on the path of the ball, and it's vertically above T. the target. Find the speed of the ball at C. Well, I'm talking about finding the speed there. The overall speed would be a tangent to its path. So if I put a tangent to its path, there it is there. That blue vector there represents the speed v. Now I can't find v directly, but I can find vx and I can find vy. So I can break that into components. I can break that into a component that goes in the x direction. So here's a component in the x direction and a component in the y direction. Just by completing the rectangle around that blue vector. So those two red components are Vx and Vy. I can work out Vx and Vy from my table, and then I can put them together using Pythagoras. Now, I'm going to need a new table because we're now talking about not landing at B, we're now talking about being at C at this point. So therefore I need a new table. Well, you can draw a table yourself. I'm not going to draw the whole thing again because the only thing that changes in my new table is the last part, because the launch speed stayed the same, of course, and AX and AY are always the same. So all that changes are these numbers here, SX and SY. They're the numbers that change. Well, my equations are V is equal to U plus AT. I want Vx and Vy. Well, write down the x equation. And you know that AX is 0. That means Vx is equal to Ux. And Ux is 25 root 3 on 2. So you already have the Vx, don't you? Because that never changes. So what then? What about the other one? Well, I need to find Vy at that point there. Well, what are the coordinates of C? The coordinates of C are, how far did I go out? Well, I went out 21, didn't I? So the coordinates of this are 21. And how far did I go down to C? I'm actually not sure. So just call it SY. But the important thing is I can fill in the table for SX. SX is 21. SY I don't know. So I can find out the time it took to arrive at C. And the reason I need to know the time it took to arrive at C is because, look at my Vy equation. Here's Vy. That involves time, doesn't it? So when I want to work out Vy, Vy is Uy, which is minus 25 halves, or minus 12.5, minus 9.8 times t. So I have to find the time it takes to arrive at the point C. Well, why don't we go to the x side of the equation and write down Sx equals Uxt. Sx is 21. Ux is 25 root 3 on 2 multiplied by t. Solve that equation for t. So you do the math yourself. You're going to slide the 2 up, multiply the 2 by the 21, and divide by the 25 root 3. Decimalize it. 0.9699 looks to be, say, 0.97 seconds. Makes sense, doesn't it? That's just before it lands. It took 1 second to land, so it's a little bit shorter of that. Now, go back to my Vy. That's minus 12.5, minus 9.8. And the time it took to arrive at C, I've just worked out to be 0.97. So now I can work out Vy. I get minus 22.006, let's say minus 22. And you know what? The minus makes sense, doesn't it? Because when it arrives here, you can see the y component is pointing down and the x component is pointing to the right, so that's positive. Now to find v finally, you want to put the vx and the vy together using Pythagoras. So the overall speed v is the square root of vx squared plus vy squared. That's the square root of 25 root 3 on 2 squared plus minus 22 squared. So anyway, I think you're safe enough to finish that off yourself and check the answer at the back of the notes. So you can see they're getting a little bit trickier, but the same technique I'm applying over and over again. Let's have a look at the 2019 question. Particle is projected with a speed of 40 meters per second from a point A. Once again, we're going to make A the origin 0, 0. A is 30 meters above the horizontal ground, and it reaches a point B. And point B, they say, it's at its maximum height, 42 meters above the ground. That gives me a very important piece of information. That means if it's at its maximum height, it's no longer going up or down. That means its velocity in the y direction is equal to 0. So I've written down there Vy is equal to 0. Then it continues on and lands at C. So I'm going to put a table together. And because I have that really important information that Vy is equal to 0, I'm going to do my table for when it arrives at B. So let's put it together. They're asking me to find, in part 1, the angle alpha. Now, when they ask you to find the angle, that's probably the hardest thing they can do in projectiles, is to find the angle. Ux is 40 cos alpha. Uy is 40 sine alpha. They're both positive, aren't they? Going to the right and going up. Ax and Ay, they're always the same. Ax is 0 and Ay is minus 9.8. Sx and Sy, remember when we're arriving at B. So the coordinates there, how far did I go out to the right? Well, I don't know. So I'll just call that Sx. How far did I go from A? Well, just look at the numbers. If A is the origin, how far above A is B? Well, it's 42 minus 30. That's 12 meters. So that means Sy is equal to 12. Now, what do? Well, have a look at both sides of the table. Missing a number there. What about here? Well, we don't know alpha, and you know we don't know the time either. So I don't really want to get stuck into that just yet. I want to use that piece of information, that Vy is equal to 0, and start with the V equation. So wherever the information leads me, that's where I'm going to go. Here's my V equation. V is equal to U plus AT in the Y direction. So let's fill in the numbers. When I'm at B, I know that Vy is equal to 0. Uy is 40 sine alpha. Ay is minus 9.8 by t. So I want to write that down with t on its own. I'll have I will have t in terms of alpha. So jump the 9.8 t to the right, or to the left should I say, and that's equal to 40 sine alpha. The time t is 40 sine alpha divided by 9.8. That's the time it takes to arrive at B in terms of alpha. Now, I'm going to go to my s equals ut plus a half at squared equation, and I'm going to do it in the y direction. So, sy, when I arrive at B, is 12. Uy is 40 sine alpha. Multiplied by the time. Here's the time that I got from the Vy equation being equal to 0. 40 sine alpha divided by 9.8 plus a half ay minus 9.8 by t squared. It's going to be this stuff here, 40 sine alpha divided by 9.8 all squared. So it looks a bit nasty, but I suppose the nice thing about it is I'm only missing one variable, alpha. So I want to solve that for alpha. So let's see how we'll do it. So I've got 12 is equal to 40 by 40. Use your calculator or your head, 1600 divided by 9.8. And sine alpha by sine alpha, that's sine squared alpha. What about here? Well, the overall term will be minus a half. There's probably lots of ways you can solve this. I'm just picking a particular way to do it. If I square the bottom, I get 9.8 squared. And if you divide that 9.8 into the 9.8 squared, you will get 9.8 on the bottom. 40 squared, that's 40 by 40. That's the 1600. And sine alpha all squared is sine squared alpha. So, I've got two terms on the right, which are sine squared alpha. There's one term, and there's another term. Now, here's just one approach for solving it. You know, this first term, the coefficient is 1600 over 9.8. The coefficient over here is a half of 1600 over 9.8. So essentially, this part of it here is the same as this part of it there. It's almost like 1x minus a half x will give you a half x. So I get 12 is equal to that term minus that term. It's 1 minus a half. That gives me a half of 1600 over 9.8 by sine squared alpha. Right, so now I'm in a position to solve for sine alpha. Bit of cancelling maybe. So that implies slide the 9.8 up to the 12. And I'm going to slide the 800 down. That's equal to sine squared alpha. I don't want sine squared, I want sine alpha. So sine alpha will be the square root of all of that. And therefore alpha, that will be the inverse sine of the square root of 12 by 9.8 divided by 800. So it's a tricky little calculation. Let me put that into my calculator. Shift sine. Square root fraction button, 12 by 9.8, divided by 800. Close your bracket. And I get 22.5 degrees for the angle alpha. So it's tricky enough. The maths in that is tricky enough. Now I've got alpha. Now I can move on. They're asking me to find the horizontal range of the particle. Well, the horizontal range, we're now talking about this particular particle landing. So the horizontal range will be from A in the horizontal direction across to C. We're talking about that distance there. I suppose we're talking about doing another table now, aren't we? We're talking about doing a table where it lands at C. Ux and Uy, they're the same, except of course we know alpha, don't we? We know that alpha there is 22.5 degrees. Will I work it out? 40 sine, 22.5, and 40 cos, 22.5 degrees. Well, you can leave it like that. You can work it out if you wish to 1 or 2 decimal places. Ax and Ay, they don't change. Now I'm talking about the coordinates at C. The coordinates at C, that's the distance you went out in the x direction. That's Sx that I don't know. That's the range they're asking you to find. And from A, how far did I go down? I went down 30, that's minus 30. So Sx is blank, and Sy is minus 30, because I'm drawing the table up now for C. So now, let me find the horizontal range of that particle. S equals ut plus a half at squared, but if it's in the x direction, it's Sx equals uxt. Ux, that's 40 cos 22.5 by the time, and the time to land. Well, that time to land, I don't have it here. So what do I have to do? I now go to the other side to work out that time to land. So I'm going to go to the Sy side and get that time. So S equals ut plus a half at squared. All in the y direction. Sy minus 30. Uy 40 sine 22.5. By t plus a half ay minus 4.9 t squared. What does it look like? Looks like a quadratic in time. So I've got to bring all my t's to one side and have 0 on the other. So I've got 4.9 t squared minus 40 sine 22.5 by t minus 30 is equal to 0. So you're going to use your quadratic equation to solve that. You're going to write down your ABC. I did it already today. I'm not going to be doing it again. I'm just going to put it straight into the formula. So t is minus b, which is plus 40 sine 22.5, plus or minus. So I've done my calculation, and let me write it down to say to 2 decimal places, 4.49 seconds. So it takes 4.49 seconds to land. Now, I want to find that horizontal range, so I'm back here again, haven't I? So I stopped there because I didn't have the time. So now I'm going to put that time in there. So now I've got 40 cos 22.5 degrees multiplied by a time of 4.49 seconds. And I get a range, a horizontal range of 165.9 meters. Final part of it, the speed of the particle as it hits the ground. Obviously when it hits the ground, it's going to stop. So you're just talking about that split second before it hits the ground. So again, when it hits the ground, you would take the velocity vector as being tangent to its path. So the velocity, something like this, that will be v. But I can't work out v directly. I can work out vx and I can work out vy. Vx and vy using my u plus at equations. This one is vx is ux and vy is equal to uy plus ayt. You know what the time is, don't you? 4.49 seconds. So I'm going to let you finish that off yourself. You can easily work out vx and vy. And how do you put them together? Using Pythagoras. So v is equal to the square root of vx squared plus vy squared. And the answer you should be getting is 46.8 meters per second. So you can see the calculations are getting a little bit trickier. But at the end of the day, it's the same thing all the time, isn't it? Set up the diagram, put your table in, and you're just using two equations, s equals ut plus a half at squared, and v is equal to u plus at. So that's the end of lesson 2. Thanks very much.